Okay, this is going to be the first of multiple parts of video that covers chapter 14-15 for AP statistics, which are the foundational rules for probability calculations. One thing about this unit, Unit 4, which actually has 4 chapters in it, 14-15, which are their main rules, 16, chapter 16, we're going to cover some things about distributions and how they can be combined to do different kinds of probability calculations. And then in chapter 17, we'll cover some standardized probability models like the binomial and the geometric model. But these foundational rules that are in chapter 14-15 are kind of the basic rules that apply throughout all of probability. Now, a lot of this will be things that you have seen at some point in the past, because I know there's probability units kind of scattered throughout the earlier math curriculum. So some of this might be new to you, but a lot of it could be familiar. I'm going to teach it assuming that we haven't seen it before. So the more that you remember from the past, the easier it'll be, but we'll explain everything fully. And I've got some places in here where we're going to integrate practice from the chapter 14-15 practice packet. This will definitely take more than one day to cover in class, so I'm going to break this video series into parts as well. Okay, so to start with, we'll define some general terms for probability. Probability is really just the relative frequency or likelihood of something happening in the long run. Anything can happen if we have a small number of trials, and we've seen that when we did sampling and we try things where we each do parts of an experiment. Every time we do it, we get a little bit different thing. But if there's kind of an underlying structure in something, if you take enough cases, eventually you'll start to see trends that stabilize over time. Consider this situation. Let's say on your drive to work, you encounter one signal light. And when you arrive at the signal, sometimes it's red, and then sometimes it's green or yellow, right? So because you don't leave at a specific time each day, the exact time you arrive at the signal is random. But there is an underlying structure in the situation. Maybe that signal light is red for 2 minutes out of every 10 minutes, and it's green or yellow for the rest of the time. And that means that 2 out of every 10 minutes, or about 20% of the time that you arrive at the signal, the light should be red and you should have to stop. Right? On any particular arrival time, anything can happen. But if you keep track of the signal over many, many, many days, like let's say 100 days, this underlying structure is going to emerge. You're going to see about 20% of the outcomes where you encounter the light will be red and the rest will be green or yellow. So there's something called the law of large numbers that says that the observed frequency of what you see happening will approach the theoretical probability that the light is 20%, right? So in any small number of cases, anything can happen. If you just track for like 3 or 4 days, you could get stopped, at the red light every time or none of the times, right? But if you look at enough cases, eventually you'll get closer and closer to the value 20% of the times you encounter the red light. So that's what probability is. It's about the occurrence of something or the frequency of something happening or the likelihood of it happening in the long run with a large number of trials. So some terms to know. First of all, we're going to use the term outcome to indicate one possible result that can occur in an experiment or something that we're doing, a scenario. So an example of an outcome would be if we roll a single die one time, maybe it's a 6-sided standard die, like 1, 2, 3, 4, 5, 6, one of the outcomes is 5. Right, so we could get a 5. Or if we define the experiment as tossing a coin twice, then we could get tails the first time and heads the second time. And since we have to do both coin tosses to complete the experiment, tails then heads would be considered an outcome. Okay, so an outcome is one thing that can happen when you complete a trial of something or an experiment. Okay, the sample space, that is the set of all of the outcomes that could occur. Okay, so for example, if we wanted to list out the sample space for the scenario of rolling a single 6-sided die, then the outcomes are 1, 2, 3, 4, 5, 6, and therefore that's the sample space is the listing of all of those things. And for tossing a coin twice, then the possibilities are heads then heads, heads then tails, tails then heads, tails then tails. So there are 4 possible outcomes in that sample space. And a lot of times when we list a sample space, we just do what's called a roster listing of the set. So a set is a collection of objects, doesn't matter the order, but we just list all the possibilities in some way. And so we're basically listing a set out, and that is one way to show a sample space. Okay. So at this point, I usually ask people just with just that to go ahead and take their required practice packet and just go ahead and complete problem number 1. So go ahead and pause the video, try this out, and what this is asking you to do is to list the sample space in each of these cases. And then unpause the video and I'll work the problem. Okay, for part A here, we're rolling 2 dice, and we're assuming, unless it says otherwise, that a die is 6-sided and all of them are equally likely, a regular old die, and record the sum of the numbers. All right, so if we roll 2 dice, what could happen? Well, the smallest outcome that we could have is we could get a 1 and a 1, and that means that the smallest sum is a 2, right? So the sample space here is going to be 2 is the smallest outcome. Could we get a 3? Yes, we could get a 3. That would be a 1 and a 2 or a 2 and a 1. Could we get a 4? Yes. A 5? In fact, we could get all the numbers all the way up to the largest sum that we could get if we rolled 2 die would be 12, because that would be if we got a 6 and a 6. And then it asked whether or not you think that these outcomes are all equally likely. The answer to that is no, right? Because there's only one way to get a 2 if you roll a 1 and a 1, right? But there's many ways to get a 7. You could roll like a 2 and a 5, or a 5 and a 2, or a 4 and a 3, and a 3 and a 4, or a 1 and a 6, or 6 and a 1. There's a lot of ways, so it's more likely you're going to get a 7 than you would get a 2. So these are not equally likely, and that turns out to be important later. Okay, let's look at B. It says a family has 3 children. Record the genders in order of birth. We're assuming a binary gender definition here of male, female. So if we have 3 children, right, what could happen? Well, you could have, let's use boy and girl. Use G for girl, B for boy. You could get 3 girls. That's one possibility, right? You could have 1 boy and 2 girls, and the boy could be first, right? Or the boy could be second, or the boy could be third, right? Or you could have 2 boys and 1 girl, and the girl could be first with 2 boys, or the girl could be second, or the girl could be last, and then finally we could have all boys, right? So if you want to list this out, you have to come up with some some sort of systematic way to list things here. What I did basically was look at all girls, and then all girls except for 1 boy, and I varied the position of the boy, or all boys and 1 girl, and I varied the position of the girl, or all boys, right? And are these equally likely to occur? Well, since it's equally likely to get a girl or a boy in every spot, actually all of these are equally likely. Every one of those 8 outcomes is equally likely. Okay, C. Toss 4 coins and record the number of tails. The number of tails. Okay, so if you toss 4 coins, the smallest number of tails that you could get would be 0, right? Now they're asking me to record the number of tails, so we're not really recording the individual coin tosses, right? We're just recording the number of tails. You could get no tails, right? Or one of the coin tosses could be tails, or 2 of them could be tails, or 3 of them could be tails, or all 4 of them could be tails. Are those equally likely? Probably not, right? Because to get no tails, you'd have to have all 4 heads. But to get, say, 3 tails, there's different ways that that could happen. You could have the first, second, and third one be tails, or the first and the third and the fourth one be tails. There's more ways to get the ones in the middle, so these are not equally likely. Okay, D, flip a coin until you get a head, or until you get 3 consecutive tails. So this has to do with specifically what happens with heads and tails. All right, so we could get a head or a tail, right? So we could get a head on the very first try. And if that's true, we would stop, it says, right? Or we could get a tail first, right? But if we got a tail, then it says keep going until you get a head, or until you get 3 tails. So we could get a tail the first time, and then we could get a head on the second roll, and that's when we would stop, right? Or we could get a tail the first time and a tail the second time, and then a head on the third case, and then we would stop, right? Or we could get a tail the first time, a tail the second time, a tail the third time, and then even though we haven't got a heads, it says or we stop when we get 3 consecutive tails. Consecutive means in a row. So this right here is all the possible things that can happen. These are all the outcomes, and this is the listing of the outcomes, the sample space. These are not all equally likely, because there's a 50-50 chance of having this happen, but there's a less than 50-50 chance of having all 3 become tails. All right, so that's the That's the idea of sample space. It turns out sample space listing is really important because I know throughout math you've heard the idea that you should always draw a picture if you can, especially with a word problem, to be able to put numbers in the picture. Well, the picture for a probability problem is the listing of the sample space. And there's different ways to list sample spaces. One way is like this with a set, but later we're going to explore things like Venn diagrams, and we'll also take a look at trees, tree diagrams, and tables. Those are basically the main ones: set listings, trees, Venn diagrams, and tables. But right now we're just making simple lists or sets. Okay, let's talk more about some terms. So a sample space is a listing of the outcomes. So we're going to define the word event to be any subset of the sample space. So some of the outcomes, but typically not all the outcomes. So for example, if I'm rolling a single die, I could define an event to be rolling an even number. And so that means out of the sample space, which is 1, 2, 3, 4, 5, 6, those are the things that could happen. The even ones are just the 2, the 4, and the 6. So I would have a subset. Only these outcomes, 2, 4, 6, qualify as even. So this an event is a subset of some of the outcomes that are in the sample space. I mean, theoretically, it could be all, but usually it's less than all of them. Okay, or if I have the sample space that we're rolling, or we're flipping a coin twice, where I could get heads, 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 tails, tails, heads, and tails, tails as the sample space, maybe I could define the event to be getting at least one tail. Well, at least one tail is every one of them except this one. So it would be the heads, tails, the tails, heads, and the tails, tails one. Okay, so we'll define a probability of an event as being some number between 0 and 1, okay? And that represents the likelihood of the event. And we'll use a capital P for probability, and then in parentheses, we'll put what it is we're finding a probability of. So generically, it's just called a letter E for some generic event, but usually we'd fill in what that event is. Like we'd say probability of at least one tail, and we'd write that inside there. Okay, so the probability is always somewhere between 0 and 1. And if you add up all the probabilities in a sample space, they all have to add up to 100% because there's a 100% chance that one of the outcomes will happen, okay? And then you can write probability in different ways. You can write it as a decimal number, like say 0.4, or you can write that as a fraction, 4 out of 10 or 2 out of 5, right? That's okay. Fractions, decimals, they're all fine, as long as there's some value that goes between 0 and 1, okay? Okay, let's look at kind of the typical problem that's talked about with a single event. We're talking about probability of an event, and a lot of times we consider selections of things. So if you have a selection of objects and you want to select some out of that. So let's say that I have a jar, and I have 3 colored balls in it, one red, one yellow, and one green, and I want to draw one ball from the jar. Okay, so what would happen? Well, the sample space would be that we could either draw a red ball, a yellow ball, or a green. So I'm using letters here to represent that. And hopefully you will agree that as long as I do this randomly, then there's an equal chance of all of those things happening. So if I wanted to assign a probability to each of these outcomes, each of them would get 1/3 of the probability. We know that the probability of all of them has to add up to 100% 1. And so if there's 3 of them, each of them get 1/3, right? So the probability of one of these events is 1/3, right? Each of these is 1/3, right? Okay, and then you may have seen this at some point in the past. Usually I call this the middle school probability formula, because the probability of, let's say, getting a yellow is, usually we say it's the number of desired outcomes over the total number of outcomes, right? So the number of ways you can get a yellow would be 1, and the number of total ways we can draw the balls are 3, and so the probability is 1/3, okay? And this works just fine. This is good as long as all the outcomes are equally likely. So we will occasionally use this, but not always, because in our class, we're going to encounter situations where these are not all equally likely outcomes. But if they happen to be, then you could just count up the number of balls that are yellow out of the total number of balls that are yellow. Okay, so if I know that the probability of getting a yellow ball, just one ball, is 1/3 here, right? And I know that all of the outcomes here have to sum up to a total probability of 1, then that means that I could represent the sample space instead of just as a listing of red, yellow, and green, I can choose to draw what's called a Venn diagram. And we put basically a rectangle that represents everything. And then we come up with some way to devote space to each of these different things. Like we could say, this circle here is going to represent yellows, and then we'll have red and green. Right? So here's the thing. If the total area in here represents all of the probability for everything, which is 100%, and 1/3 of it is in here, then that means 2/3, the other 2/3 is out here, right? So taking the opposite of something is called the complement. And so if I wanted to say, what's the probability of getting any ball other than yellow, right? Well, that's going to be 100% minus the probability of getting a yellow, which is 1/3, and therefore is 2/3 chance, right? And there's different ways to write this opposite of yellow, okay? The one I'm going to use in class is this one. If I want to mean not yellow, I'm going to use whatever symbol I'm using, like for yellow, and I'll put a line over it. That means the opposite of yellow, so anything other than yellow. But sometimes people will encounter in textbooks a Y with a prime, a little apostrophe next to it like that. And even some books, especially more advanced probability textbooks, will put a C for complement up here. So all three of these symbols mean not yellow. Okay, the same thing, okay? And so you can kind of think of it as, you know, if this part right here is yellow, then the probability that we're not yellow is just everything else. And so it would be 100% minus the 1/3 to get the 2/3. Okay, so basically this is a definition of the word complement. Okay, and so let's do another case. So we know that if we had one red, one yellow, one green ball, and we had the outcomes there, red, yellow, green, the probability of each was 1/3, right? That's, we mentioned, only true for equally likely outcomes. What if I just changed the jar like this? What if I said that there's 4 red balls, 3 yellow balls, and 1 green ball? Now the probability when I draw one ball out of here is not equally likely of getting a yellow, red, and a green, right? Each of the individual balls is correct, right? But hopefully you'll agree that there's 4 out of 8 chances to get a red ball. There's 3 out of 8 chances to get a yellow ball, and there's 1 out of 8 chances to get a green ball. Now, if you add those up, 4 8s, 3 8s, and 1 8, those things do add up to 100%, to 1, right? And now the probability of yellow is not 1/3. Even though yellow is 1/3 of the possible outcomes, those outcomes are not equally likely. So we can't use this formula that just says, you know, count up that there's 1 yellow letter here and there's 3 letters. It's not 1 out of 3 because there's 1 out of the 3 possible outcomes. We have to go back to the individual balls and count the balls. Now, it is true that each ball is individually equally likely. So if I counted balls, right, 3 yellows out of 8, that would be correct, okay? But the point is, I can't just use a sample listing that doesn't account for the probabilities being different. If the probabilities are different, I have to find some other way than just counting yellow is one of the 3 symbols. Okay? All right. So at this point, we have enough information for you to stop and try problems 2 and 3. So go ahead and pause the video, go to your chapter 14, 15 required practice packet and try problems 2 and 3, and then unpause the video. Okay, so I'm going to go ahead and work these. Problem 2 says the American Red Cross says that 40% of the U.S. population has type A blood, 11% has type B, 4% has AB, and the rest has type O. If a person from the U.S. is chosen at random, then what's the probability that they will have type O blood? Well, what I could do here is maybe make a listing of the outcomes, right? I know that the sample space, they said, was we could have A blood, B blood, AB blood, or O blood, right? And they told me some probabilities, right? So I'll just write some probabilities down here. I know that 40% of the population has type A blood, 11% has type B. And by the way, you can write probabilities as percentages like that, 11 with a percent sign, or in percentage, it's the same with a decimal, but you shift the decimal point 2 over. So I will tend usually to use decimal, but sometimes you'll see it written like that, right? 4% of the population has type AB blood, and we're trying to figure out how much, what's the probability that, or what percentage of people have type O blood. So hopefully you solve this by saying that these things have to add up to 100%, right? So these things have to add up to 100%. So if you added up these numbers, the 0.4, the 0.11, and the 0.04, you end up getting that that's 55%. So what's left here is 100% minus 55% is the other 45%. So we have to have 45% of people getting type O blood. Otherwise, this wouldn't be a valid probability model because all these probabilities must sum to 100%. Another way to write that would be to say the probability of having type O blood is 1 minus the probability of everything that isn't O, right? So it's 1 minus the probability of everything that isn't O, which is 55%, and therefore has to be 45%. So just using some symbols here to be familiar with the symbols. Okay, and then the number 3 problem said, okay, we've got a single die that's rolled one time, and we want to find the probability of various things, right? So a good idea is to list out a sample space, right? If we have a single die, we could get a 1, a 2, a 3, a 4, a 5, or a 6, and these are all equally likely, right? So if these are all equally likely to occur, then the probability of beginning a 4, I could use that formula that says it's the number of desired outcomes over the number of total outcomes, because these are all equally likely. So that would be, for part A, a 4 represents one of the outcomes out of 6. So probability is 1 out of 6. For B, an even number. So which numbers are even? Well, the even numbers are 2, 4, and 6. So there's 3 even numbers out of 6. So you can write that as 3 halves, or you can write it as 1 half, or as 0.5, or as 50%. All of those are valid ways to write the answer. Okay, for part C, it says, what's the probability of a number greater than 4? So the number greater than 4, well, the numbers that are greater than 4 are 5 and 6. Greater than 4 doesn't include the 4. So it's 2 out of the 6 cases, or 1/3, right? And then for D, it says a probability of a number less than 7. Well, actually, all the numbers are less than 7. So all 6 out of 6 cases, or 100%, or 1. And then finally, for E, it's the probability of a number being greater than 0. Same thing. All these numbers are greater than 0, so all 6 outcomes out of 6. So those last two would both be 100%. Okay? All right. Okay, let's go back to the notes then. So now we're going to define something called conditional probability. This is also a hugely important thing, and this is covered in probably Algebra 2 or maybe pre-calculus, not sure. It's definitely covered in Honors Algebra 2, which is the combination of those two classes. Let's say we asked 60 girls and 60 boys at a local high school what their favorite entertainment activity was, okay? And we just limited them to these 3 things. Do you like to read a book, play video games, or watch Netflix? And then we kept the girls and boys separate. And again, I'm going to make a general comment here once. You know, I know that in this day and age, there's different ways to think about gender. But gender is such a convenient thing for us to use as a way to divide people up. And so a lot of the examples in this class will be divided into genders, girls and boys. I don't mean to imply that those are the only 2 genders. You know, I know that nowadays we have other ways to define gender, but if you just assume that people have been divided into girls and boys, then we're just going to go with that. It doesn't mean that there could be others. And remember, whenever we study something, we have to specify what part of the population we're talking about. It could be that non-binary people are just not included in the data set, and that's fine. All right, I won't bring that up a lot, but I just want you to know that, you know, it's not a judgment kind of thing. It's just the data that we have. All right, so if we had this outcome right here, and this is another way to show a sample space. Basically, we have combinations of gender and favorite activity for these people, and we've kind of grouped them together, and these represent counts. So this is like a contingency table that we studied way back in Unit 1. And then what we have at the end here is not the data, but these are summaries that show the totals of each row and each column. So there's 100 people, a total of 60 girls, 40 boys, 22 people like to read a book, 32 like total to play video games, and 46 Netflix. All right. So we could ask various questions about probability, and each probability would be the percentage, which is a ratio of two numbers from the table. For example, I could ask, if I select a student at random from this group, what's the probability of selecting a girl? Okay, now each student in here is equally likely to be selected. So this is an equally likely cases probability. So that means I could use the kind of middle school formula that we're going to take the number of ways the desired outcome could happen divided by the total number of outcomes. Okay, so I'm finding the probability of a girl. Then that means that the total number down here is going to be the entire sample space. In other words, the entire table. And so if you add up all of the outcomes there, there's a total of 100 outcomes, 100 students that can be chosen. And since we want the probability of someone being a girl, then we would say, okay, within that sample space, how many of them qualify as girls? And that would be 60. You could add that up. So it would be 60 out of 100 or 60%. Right? Now, when we do this, this is referred to as finding a simple probability, in contrast to what we're going to do next, which is called a conditional probability. Okay, so when we're using the entire sample space, then we call that a simple probability, and the number on the bottom is the total number of outcomes here. Okay. Okay, but I could ask this. This is another simple probability. If I select a student at random, what's the probability of selecting a student who likes video games? Here, I would write the probability statement this way. I'm finding the probability of finding somebody who likes video games. And that means that I'm taking out of all of the people, all 100 people, right, how many of them like video games? That happens to be these 32 right here. So 32 out of 100, or 32%. Okay, so far two simple probabilities. But what if I ask this? What's the probability that a girl prefers video games? Okay, now in this case, I'm actually imposing a condition. I don't want to consider all the people. This right here is called a condition. And sometimes it's hard to figure out which of these parts, the girl part or the video games part, is the condition. But for now, just assume that this is the condition. And what that means is that we're not going to consider all the students. We're only going to consider the girls. So that means we're restricting ourselves. Okay, now when we do that, that is called a conditional sample space. Okay, so we're not taking the entire sample space. We're just taking a portion of the sample space that meets the condition. And so that means we would say it's only out of the 60 girls. And then we would have to say, okay, we only want to deal with girls. So we're not going to, in the video games column, we're trying to find the probability that someone likes video games. But we're only going to take the part of the girls that like video games. So it'd be 12 out of 60, which turns out to be 20%. Now, this is called a conditional probability when we impose a condition this way. And there's two things to note about it. One is that we alter the way we write the probability statement. We say it this way: the probability that somebody likes video games, given the condition, this line, that we're talking about a girl. Okay, so the part that comes after this line is the condition, and the part that comes first is the thing we're finding the probability of, the event itself. Right, so we would write that this way: that what's the probability of someone liking video games given the condition that they're a girl? And then the thing I want you to note about that is that the girl part, the condition, in this case the girl, is always a part of the sample space, and then the event is always a part of the conditional sample space. So this is a subset of a subset. Right? The condition forms a subset of the entire sample space, and then the event is a subset of that subset. Okay? And then that means that when you form the fraction, right, the condition, the bottom of the fraction, is the total number of elements in the conditional sample space. And then the numerator of the fraction is just the part of that conditional sample space, the count in that part. So it's a subset of the entire sample space. All right, the bottom of the fraction is related to the condition after the line. The top of the fraction is the part inside there that's related to the event we're finding the probability of. Okay, so let's try this one. What's the probability that a student who prefers watching Netflix will be a boy? Okay, so there's two parts to this, right? There's Netflix and there's boy. Which of these things is the condition, and which of these things is the thing we're finding the probability of, the event? That can actually be pretty tricky. Okay, the way I think of it is this: if you can find a part of this to kind of put in parentheses, what's the probability that a student, in parentheses, who prefers watching Netflix will be a boy. And you imagine that you temporarily just disregarded the thing in the parentheses. If the rest of the sentence makes sense, then that means that the part that's still in the sentence is the event. In other words, if I removed that parentheses part, this says, what is the probability that a student will be a boy? That means I'm finding the probability that somebody is a boy, okay? Okay, but the parentheses part is imposing a condition that they like Netflix, okay? So that's one way to kind of figure out, well, which part is the event and which part is the condition. The other way to find it is you can look for the verb in the sentence. Try to find the verb. What is the probability that a student who prefers Netflix will be a boy? Be, actually, to be is a verb, right? This part, this is just part of the general part question, right? But in terms of describing this, be is the verb. Being a boy is what the verb is. That's the action. And so the action, the verb, is always defining the event. And the part that isn't attached to the verb like that is the condition. Okay, so you have to go through a process to figure out which one is which, right? And let's, now that we have that, figure that out. That means that the bottom of this fraction is going to be defined by watching Netflix. Let me use a different color here. Watching Netflix is a portion of the sample space. So I would take the watch Netflix people, which adds up to a total of 46. And then out of that, how many of those people are boys? That's this right here. So it would be 16 out of 46. Okay. Hopefully that makes sense, right? I'd like to figure out the bottom of the fraction first by finding the conditional sample space and counting that in some way. And then within that sample space, which part meets the criteria to be the event? In this case, boy out of the Netflix people. All right. Or here's another one. What's the probability that a student is a girl if they prefer either playing video games or watching Netflix? Okay, so the verb in this sentence is, and so this is about is a girl. So we're really finding the probability that somebody is a girl. Okay, but it seems to be imposing a condition. So what's the condition? Well, the condition is that the person either plays video games or watches Netflix. So they like video games or they like Netflix. Okay. Okay, so to be in the condition here, they like video games or Netflix, which is all these people here. So on the bottom of our fraction, we would have to add up 12 and 20 and 30 and 16, which turns out to be a total of, let's see, what is that? 78. Okay. And just making sure I got this right. And then in the numerator, I've got to say, okay, which ones the event is that we're finding the probability of someone's a girl. So that's going to be these numbers, the 12 and the 30 added up. So we've got 42. So it's going to be 42 out of 78, right? Which turns out to be 5385. So given that someone likes to do something other than reading a book, either video games or Netflix, the probability that a person in that group is a girl is about 54%. All right. So it does matter which part is the event and which part is the condition. All right. If you, for example, say, what's the probability of someone being a boy given that they like video games? Well, the video games part now is the condition. So the video games is 32 people, and then the boy is the event. So 20 out of 32. That's about 62.5%. But if I reverse that, the probability of someone liking video games, given that they're a boy, now the conditional sample space is all the boys, and we want the video game players out of the boys. So 20 out of 40, which is 50%. So it's very important. You can't just arbitrarily reverse these things, right? Okay, at this point, you should be able to stop and do problems 4, and 5. Okay, so go ahead and try that. And then unpause the video, and I will work all of those problems. And then that's going to constitute part 1, okay, end of part 1. So give that a try. Try problems 4 and 5. Okay, let me go ahead and work these. And, I'm going to copy these to 2 different pages so that we can We can spread these out a bit. Okay, in this first one, we're just going to work problem 4. Hopefully you've already tried this problem. All right, we've got a listing here of a sample space. They already listed it for us. They gave us 4 outcomes and the associated probabilities for each of the outcomes. All right, so this is about the likelihood of somebody getting cancer and also smoking. So some people smoke and get cancer. That happens 5% of the time. Sometimes people smoke and don't get cancer. That happens 20% of the time. Sometimes people don't smoke but still get cancer. That happens 3% of the time. And then sometimes people don't smoke and don't get cancer. That's most frequent. That happens 72% of the time. So part A here is asking us to find the probability that an individual gets cancer given that they're a smoker. Okay, now if you see the word given, that's another way where we're defining a condition. That's telling me, imposing a condition. So we want the probability that somebody gets cancer given that they're a smoker. Okay, so that means that first we'll use the smoker part to define the bottom. Okay, now the smoking part, well, smoking is part of both of these two situations here, right? And I don't have counts here like I had in that last table. I have probabilities. But when we form these things, since we're going to divide top and bottom by that, if we take those objects out of the same table, whether they're counts or probabilities, we're okay. So you can actually fill the numerator to the denominator in with probabilities. So what I'm going to do here is say there's 2 ways that somebody can smoke. This is the conditional sample space here. And so we'll talk later tomorrow about why this is true, that we can add these. For right now, just trust me that we can add these 0.5 and 0.2. And then out of that, which one meets the criteria to be the event, which is cancer? That's just this group here. So this is 0.05. So it turns out to be 0.05 out of 0.25, which ends up being 20%. So if someone smokes, there's a 20% chance they're going to get cancer. Okay? All right, let's look at part B. Part B says, what's the probability that an individual does not get cancer given that they're a smoker? Okay, so what's the probability that they don't get cancer? I'm going to use this line, the opposite of cancer, not getting cancer, given that they smoke. Okay, so that means we would still have the same 0.05 plus 0.2 on the bottom of smokers, but now we're going to be taking the people that don't get cancer, which is this part here, the 20%. So that would be 0.2 out of 0.25, which turns out to be 80%. Okay. Okay. So if you're a smoker, there's a 20% chance you're going to get cancer and an 80% chance you're not going to get cancer. Okay. Let's work on, let me erase the table here, and we'll work on the C and D. Okay, for part C, it says, find the probability that an individual gets cancer given that they do not smoke. So if they don't smoke, I'm going to use the complement of smoke, not smoking. Okay, so now we're talking about all the non-smokers. These are the non-smokers. So 0.03 plus 0.72, there's a total of 75% of people that don't smoke. And then what's the probability that somebody gets cancer? Well, that would be the cancer people. So 0.03 out of that, 75%. And if you compute that, that turns out, if you run it in a calculator, it'd be 4%. So if you don't smoke, then there's only a 4% chance of you getting cancer. Okay. And then for D, we're finding the probability that a person does not get cancer given that they do not smoke. I'm using this complement term again, right? So we're going to be saying out of the non-smokers, 0.03 plus 0.72, which is 0.75. This time we're talking about the people who do not get cancer. That would be this group here, the 0.72. Right? So 0.72 out of 0.75 is 96% chance. Okay. So when you first look at this table, you might think, yeah, people still get cancer even when they don't smoke. Or, you know, there's a 20% chance that somebody smokes but doesn't get cancer. That doesn't sound too bad, right? But when you look at it this way, where you find these conditional probabilities, if someone smokes, they have a 20% chance of getting cancer. But if someone doesn't smoke, they only have a 4% chance of getting cancer, right? And if you do smoke, you do have an 80% chance of not getting cancer. It's still true that most people don't get cancer. But if you don't smoke, that rises to 96% chance, right? So your chances are much better of not getting cancer if you don't smoke. Okay, that's a number 4. Let's take a look at number 5. Okay, in number 5, it says the table below shows political affiliation of American voters and their positions on the death penalty. And so we've got people were either told they could choose that they favor the death penalty or oppose it, and then they divided people into Republicans, Democrats, and other. And these are all percentages. So these are probabilities here. All right. A says, find the probability that a randomly chosen voter favors the death penalty. So it doesn't seem to be implying any condition there. We're just finding the probability that somebody favors the death penalty. So that means that the bottom of this table, we're not imposing a condition. So it's the entire table. And if you add all these up, they add up to 100%, right? So it's 0.26 plus 0.12 plus 0.24 plus 0.04 plus 0.24 plus 0.1, which turns out to be 100% because these are all probabilities. And then now we want the event. Now the event is the probability that somebody favors the death penalty. That's this portion of the table. So we would have to add up 0.26 plus 0.12 plus 0.24, right, which turns out to be 62%. So 62% out of the total. There's a 62% chance that any individual person would say they favor the death penalty. Okay, let me erase the table again, and we'll do the next one. So B, find the probability that a Republican favors the death penalty. Okay, so we've got two things here, Republican and death penalty. Which of these is the condition and which is the event? Well, looking at for a verb, I'm seeing favors as a verb here. Favors the death penalty. This is the event over here. A Republican seems to be the condition to me. So I believe we're finding the probability that someone favors the death penalty given that they're a Republican. And actually, I recommend that you write out this every time because especially with conditional probabilities, this really helps you get the fraction correct, because if you get this written out, you know that the bottom of the fraction is going to be the condition. And so now I know that I should circle all the Republicans to make the bottom of the fraction 0.26 plus 0.04, right? So that's going to be 0.3, 30%. And then how many of the people favor the death penalty, but staying within the conditional sample space? Now that's 0.26. So 0.26 out of 0.3 is 87%. So that means, given that you're talking only to Republicans, now 87% of those people favor the death penalty. Okay, and then let's take a look at C. C says, what's the probability that a voter who favors the death penalty is a Democrat? So is the verb there, is a Democrat. We're trying to find the probability that somebody's a Democrat, given that we're talking only to voters who favor the death penalty. So now favoring the death penalty would be the condition. And so that means we would have to say, all right, now the conditional sample space from the bottom here is favoring the death penalty, which is this group. That's 0.26 plus 0.12 plus 0.24, which turns out to be 0.62. And then the Democrats are just this part here, the 12%. So it's 12% out of 62%, which turns out to be 19%. So probably not surprisingly, if you follow politics, if you're talking only to people who favor the death penalty, probably only 19% of those people are going to be Democrats. Okay. All right, so that's how we would do 4 and 5, and that's where we're going to stop the video for part 1, because that'll roughly correspond to the first day of instruction.